Today I will be introducing our group project, designing the next generation of smart devices using two-dimensional materials. Today there's a digital revolution shaking up societies around the world. This revolution is driven by an exponentially increasing amount of data, which requires a solution to the ever-growing data storage demand. Data storage and data mining capabilities permeate every inch of the modern economy. Hospitals must analyze data to save lives, law enforcement uses data to prevent and prosecute crime, and businesses need data to improve customer satisfaction and stay competitive. Such operations are increasingly challenged as the world data production soars higher year after year. Despite most data being routinely discarded as quickly as it is produced, there is growing demand for storage capacity among consumers, enterprises, and governments. Since the first commercial use of magnetic tape in 1951, the existing storage technologies have been pushed relentlessly for optimal performance. However, as all things are, they are bound by intrinsic limitations of bulk materials. This has led to the search for new technologies. As device sizes approach atomic scales, condensing them becomes more difficult. For example, the trend of transistor sizes reducing by almost half every 2 or 3 years is reaching a fundamental limit. This presents a key issue for semiconductor industries who must now consider different technologies. Spintronics has become an exciting new area of research, seeking to exploit the spin angular momentum of electrons as an additional degree of freedom to store, process, and transfer data. Spintronic devices may be realized with the development of many 2D materials, and so could become a key route for the future of improving computational power. This review will explore how 2D magnetic materials can be created, studied, and applied to ultra-compact data storage and other exciting challenges. But first, a brief overview of some relevant concepts in magnetism. Magnetism refers to a class of physical phenomena that arise from the electromagnetic interactions due to the movement of charged particles and the intrinsic spin of electrons from which magnetic moments arise. The electrons in materials can be imagined conceptually as tiny magnets, with two opposite poles defining its magnetic field associated with the spin and orbital motion. Magnetization arises when these subatomic magnets are collectively aligned as a result of quantum mechanical coupling. Diamagnetism and paramagnetism refer to tendencies in materials for spins to anti-align or align with an external magnetic field, respectively. In ferromagnetic materials, all spins tend to spontaneously align in a single direction, resulting in a permanent magnetic moment. In antiferromagnetic materials, neighboring spins tend to anti-align, resulting in a vanishing overall magnetization. Ferromagnetic and antiferromagnetic materials lose their long-range ordering above a critical temperature known as their Curie temperature. Most magnetic 2D materials discovered to date have a critical temperature well below room temperature. The design of high-temperature 2D magnets is a major challenge in the field and the subject of ongoing research.
The topics we'll be focusing on are ab initio and the computational methods used to discover and study these 2D materials, the spintronic applications of said materials and how spintronics work, how they are exfoliated and produced in the real world, the magneto-optical effects they rely on to be studied and applied, and some imaging techniques currently used to further develop our understanding.
When studying magnetism, especially the smallest of scales, one needs to build a framework that explains the results we see and allows us to make predictions, as is the basis of all modern science. We call this ab initio, which roughly translates from the Latin, from the beginning, and we all know how much scientists love to use Latin in naming conventions. These methods, i.e. from first principles, run into a quintessential problem in science, however, called the many-body problem, MBP, which is often found when shifting perspectives from the microscopic to properties in bulk. Precisely, magnetism in bulk is caused by the sum of all the magnetic moments from the electrons in the material, which can themselves be conceptualized as tiny bar magnets. Thus, we have developed ways to model the vast number of interacting electrons depending on what we wish to study. Usually these are split into qualitative, such as the nearly free electron fermion gas, which treats electrons as independent pseudo-gas particles, and quantitative descriptions, such as density functional theory, DFT, which studies n electrons as a set of n one-electron Schrödinger-like equations, also known as Kohn-Sham equations. Figure 2 on the board shows a diagrammatic representation of the difference between the many-body problem on the left and pseudo-independent electrons in a central potential on the right. To go further, however, we utilize the formidable power of computers, which allow us to marry lengthy models and physical intuition into accurate predictors that aid our study of magnetism. And most recently, with the emergence of artificial intelligence and machine learning, we have become capable of predicting new properties and materials that can power the next generation of two-dimensional magnetic devices we are hereby presenting. In our report, we outline two of the most widespread models for studying magnetism, namely the Ising and related Heisenberg models. In a similar form as shown, both include products of electronic spin, S, and thus directional magnetic moments. Think again of tiny bar magnets. Having been first devised almost 100 years ago, and with comparatively rudimentary physical knowledge, their current relevance exemplifies the usefulness of using ab initio theory to underpin our contemporary understanding of magnetism. However, and also in large part thanks to the support of modern computers, these models are often expanded and corrected to include new and exciting physical phenomena, as is the case, for example, of the energy degeneracy, i.e. similar energy levels, introduced into the Heisenberg model through the biquadratic higher order interaction shown on the board, which is the second order term, which is of one higher order than the linear Heisenberg model shown on the board. And it's actually quite of crucial importance when studying 2D magnetic materials, even though it appears to be largely absent when studying the same materials in bulk. Expanding our understanding of magnetism, as outlined previously, has also opened the possibility of accurately predicting and modeling the next generation of 2D magnets, not yet observed experimentally. We employ a concept called high throughput, for which two philosophies exist. On the one hand, we might search for new materials which we predict exhibit a desired property, as might be the case for 2D magnets retaining their magnetism near room temperature, i.e. have a high Curie temperature. While on the other hand, we might start with known monolayered magnets, like for example Cr2Ge2Te6, also referred to as CGT, look at figure 3 for clarity, and then look for feasible materials with the same molecular form, exhibiting the desired magnetic properties. All in all, having come a long way in explaining the seemingly intangible force of magnetism, we have learned to compound existing knowledge with new technologies in order to study the two-dimensional realm of monolayered magnets, in turn paving the way for these exciting materials to continue solving many of the problems we currently face, from the exponentially growing need for smaller and more informationally dense data storage to faster and more capable computers powered by spintronics.
One such example of these smaller and importantly scalable storage devices is Magnetic Random Access Memory, or MRAM for short. This is a long sought after device that has been fully realised and put into mass production by companies such as Samsung as recently as 2019. 2D materials, when combined with spintronics, basically electronics where the spin of an electron is also used, has great potential for the development and improvement of such devices. MRAM devices are based on an observed process known as magnetoresistance, where the resistance through a system changes based on the magnetic properties of the material being passed through. One such form of this is tunnel magnetoresistance, which occurs in a system such as that pictured, called a magnetic tunnel junction. In such a system, we have some insulating material separated by two ferromagnets. The bottom ferromagnet is pinned so that its magnetization direction cannot change and is known as the fixed layer. The other layer is known as the free layer, as its magnetization direction can be switched using an external magnetic field, for example. When the net magnetization of these two layers are aligned, current can flow easily from source to drain. However, when the magnetization of the two ferromagnetic layers is opposite, the current is restricted. This can be understood by looking at the states in which an electron can occupy in the ferromagnet. The number of states electrons of different spins can occupy is different depending on its magnetization direction. There are more states available in the direction the ferromagnet is magnetized in. As such, bringing two of these ferromagnets together in a magnetic tunnel junction, if the two magnetized magnetization directions are not aligned, then electrons which are in the fixed ferromagnet have a low probability of tunneling into the free ferromagnet, due to the low number of states available to them. When the layers are aligned, however, there is no restriction in the number of states available, and so current may flow easily. Such a device can be controlled using an external magnetic field, changing the free layer to adjust the resistance through the device. A magnetic tunnel junction is perfect for storing information in the form of a bit without volatility, in other words, without needing to provide an electrical current through it, as with more widespread RAM devices. And so by combining many such magnetic tunnel junctions, we can create a useful magnetic storage device. A computational bit is represented ideally by a zero resistance on state or an ideally infinite resistance off state, and so the difference in resistances between aligned and anti-aligned states of a magnetic tunnel junction should be high. The original discovery for tunneling magnetoresistance found only a small percentage difference in the on versus off state current. This is quantified via a magnetoresistance ratio, defined as the difference in resistances of the parallel and anti-parallel cases divided by the larger resistance anti-parallel case. Basically, higher ratio, greater difference in the on versus off current through the device, and so a better device. More recently, 2D materials have been used to allow for much higher magnetoresistance ratios of over 1,000,000%. But these have only been produced for low temperature systems and so currently are difficult for implementation in real-world devices. But the use of an external field to switch such devices has been shown to not be a scalable method, as we can see from the purple line here. For smaller junctions, a larger current is needed for switching. Fortunately, we can make use of angular momentum conservation to create a more efficient method of switching. By passing a spin-polarized current through one of the ferromagnetic layers, where the polarized current has spins in the direction that the ferromagnetic layer is to be switched to, the small effect of each electron passing into the layer, transferring some small component of angular momentum, can, with enough electrons, so high enough current, be used to flip the entire ferromagnetic spin direction. The scalability of this method, known as spin-torque transfer, is intuitive. The more thicker the material in use, the more higher current spin polarized electrons that must be passed into that material to change its alignment. Spin-torque transfer then, when combined with 2D materials, offers exciting potential for a very low power switching technique at small scales, and hence gives rise to real-world devices such as spin-torque transfer MRAM. The combination of such a device with very low dimensional materials presents exciting potential for high storage density, low power usage devices, ideal for the next generation.
These exciting applications depend on experimental methods which can produce high-quality samples in large enough volumes for mass production. We'll look at a few such methods in the next slide and discuss their advantages and disadvantages. Many 2D materials are chemically unstable in air, especially magnetic ones such as chromium triiodide. This presents additional challenges to production because the atmosphere needs to be carefully controlled. This can be achieved with the glove box, shown below. This is a chamber with a controlled atmosphere, such as argon, and gloves for manipulating the sample. Once the samples are produced, they are sometimes capped with a thin protective layer such as hexagonal boron nitride, an inert 2D material with a structure similar to graphene. In this case, researchers need to check whether the properties of the samples are intrinsic to the 2D material or are due to interfacial effects between the sample and capping layers. A simple and widely used method is mechanical exfoliation. For background, 2D materials come from layered van der Waals parent compounds. In mechanical exfoliation, adhesive tape is used to repeatedly strip layers from a sample with the aim of obtaining a single layer. This method was famously used with Scotch tape to produce graphene, which is single-layer hexagonal carbon, in 2004. Although mechanical exfoliation can produce high quality and large area samples, it has a low yield and is highly labor intensive. For that reason, it is thought to be unsuited to the kind of large-scale production which would be needed for mass adoption of 2D material technologies, at least in this form. An alternative to mechanical exfoliation is liquid phase exfoliation, which is carried out in a solvent and produces a suspension of nanosheets. The main advantage of this method is that it is potentially much more scalable since it targets all layers of the parent compound and can be carried out in large batches. Some liquid exfoliation techniques work on the basis of intercalation, in which guest compounds are chemically inserted between the layers of the parent compound, weakening the interlayer attraction. Other methods rely on the fact that some materials naturally contain positive ions between the layers. These can be exchanged for bulky organic ions, increasing the interlayer separation. To pull the layers apart, sound waves can be applied to the sample in a process known as sonication. This produces a suspension of exfoliated layers as well as some unexfoliated remains of the parent compound. These can be removed by centrifugation, which separates out the lighter parts of the suspension. The nanosheets can be separated out from the solvent by filtration through a membrane. For example, PTFE is used for this purpose and stands for polytetrafluoroethylene. The main alternative to exfoliation is thin film growth, which refers to a set of techniques in which the 2D sample is grown onto a substrate, which is a base material for the sample, usually from a vapor. The two main techniques for this are chemical vapor deposition and molecular beam epitaxy. These are both widely used in the semiconductor industry and more recently in the production of 2D materials. Between these two, chemical vapor deposition generally offers lower cost and higher yield. It is potentially another scalable technique, although molecular beam epitaxy usually offers more control over quality. We've decided not to look further at thin film growth in this presentation due to time constraints, but please see our report for more details on these. Once samples have been produced, there remain further experimental challenges to producing useful devices. These include transferring samples to a new substrate, applying protective layers, or assembling several 2D samples into a compound device known as a heterostructure. Here we will go over a few such transfer techniques. They generally combine an optical inspection system such as a microscope or a camera with a zoom lens with a micropositioning system. The first technique we'll look at is the PMMA carrying layer method, which is illustrated below. PMMA is a hydrophobic polymer and stands for polymethyl methacrylate. First, a substrate is coated with a water-soluble polymer layer. This is then covered with a PMMA layer and the flake of interest is exfoliated onto it. The entire stack is submerged in water, dissolving the water-soluble layer and leaving the hydrophobic polymer floating at the top, carrying the exfoliated flake. The PMMA covered side is attached to a glass slide, which is used to position the flake onto its new substrate with the help of the micropositioning system and microscope. Finally, the glass slide is gently removed, leaving the isolated flake on its new substrate. The final technique we'll look at is called the wedging transfer method. First, the flake is exfoliated onto a hydrophilic substrate such as silicon dioxide, which has been coated with a hydrophobic polymer. The stack is again immersed in water, which is attracted to the hydrophilic substrate. This separates it from the hydrophobic polymer coating, which remains floating at the top carrying the flake. The water is then pumped away, bringing the polymer film in contact with a new substrate below it. Its final position is adjusted with a micropositioning system. Finally, the polymer film is dissolved, leaving just the flake on its new substrate.
To be able to utilize the materials created by the aforementioned methods, you need to be able to study them. Due to the magnetic nature of the materials we're interested in, it would be useful to try to utilize this property to further study said 2D materials. This is where magneto-optics come into play. Magneto-optical effects are effects in which electromagnetic radiation is altered, usually by changes in polarization and intensity, by interacting with magnetic media. They are an essential part of studying 2D materials due to the interactions between light and material giving lots of context about the material properties, such as its magnetic order and spin behavior. While they are known for their use in studying these materials, they have also shown use out with the lab in the past, which will be discussed a little bit within this presentation. One such effect is that of the Faraday effect, discovered in 1845 by Michael Faraday, which induces rotation of polarized light about its propagation axis, that's the axis it's traveling along, when passing through magnetic media, as can be seen in the figure below. The magnitude of this rotation can be determined by strength of the magnetic field, wavelength of the light, and the length, temperature, and Verde constant, which is a characterizing constant of the intrinsic properties of the media. The Faraday effect doesn't have as many applications as the later mentioned magneto-optic Kerr effect. This is due to the requirement that the Faraday effect must penetrate through a material to polarize the light, and due to most materials that we're interested in, 2D magnetic materials, being metallic and reflective, this causes a large issue as the light propagating through decreases exponentially with the thickness. When you discuss 2D materials, though, this issue becomes less prevalent, due to the thickness being minute, only 2 dimensions. Now this raises another issue. With less material to penetrate, does the effect become negligible due to the lack of material? This appears not to be the case, as studies in 2D graphene in the past and other materials have shown Faraday rotation up to 1.5 degrees. The possible uses for Faraday-based tech is rather vast, as it has been widely used for quite some time in things such as Faraday isolators, which act like LEDs in a manner. They only allow light through in one direction via polarizing filters. One possible use is this anti-bleed screen, as can be seen in figure 3, where light is allowed to be passed through both filters via the magnetic media, as is the red, but the blue light isn't allowed to pass through in the opposite direction, as it's still polarized in a manner that doesn't allow it. It's not reversible, basically. It doesn't polarize back. Much like the Faraday effect, the magneto-optic Kerr effect, or the MOKE for short, polarizes light by reflecting off the magnetic material rather than propagating through it. This effect of reflection rather than propagation allows for more practical use cases than the Faraday effect, as the emitter and detector can be on one side of the material and you don't have to worry about losing intensity via propagation. There are multiple types of MOKE, as can be shown in the figure on the slide, which are based on the direction of the magnetic field, the red lines here, with respect to the polarized light. But in this talk we'll be considering the polar MOKE, as it is the most widely used when studying 2D materials. The MOKE is useful for finding information about the material's magnetic order and spin behavior, which helps us learn about the capability of certain materials for things like spintronic devices. Examples of this talked about within our paper are monolayer, which is meaning 2D, one layer, chromium iodide, and manganese phosphorus triselenide, which I will not pronounce again. Both have had their magnetic properties studied extensively with the MOKE and are found to have controllable magnetic properties to some extent. Beyond usage in the lab, MOKE has seen use in magneto-optical drives in the past, which have sadly fallen into irrelevance. The possibility of future 2D storage and processing devices based on this magneto-optical technology, using these newly researched 2D materials, will allow for small form factor and exceptionally dense information processing and storage devices. On a bit of a more fun detour, the Cotton-Mouton effect, discovered in 1907 by Aimé Cotton and Henri Mouton, who I'm sure are rolling in their graves over that mispronunciation of both their names, is best described as the magnetic birefringence of a material, in which a material's refractive index is dependent on the orientation and polarization of the light, as well as the magnetic field applied to said material. While its usage is less focused towards smart devices in terms of data processing and storage, as is considered for the MOKE, it has been seen as useful in other cases, such as in the figure shown below, in which 2D magnetic plates of graphene were suspended in a solution and were able to become an exceptionally effective magnetic birefringent material based on rather low magnetic fields and the orientation applied. Applications for this are quite vast, but the paper research gave quite a few good examples, such as a graphical writing board or a highly sensitive magnetic field detector. The writing board can be seen here almost like an Etch-a-Sketch, which is quite a fun, novel idea for such a thing. On to the last effect discussed in this section. The Zeeman effect is the magneto-optical splitting effect, in which degenerate energy levels of a material are lifted via an applied magnetic field, as can be seen in the figure below, where the 2p level is split into 3, the 2p plus 1, negative 1, and naught, due to the application of a magnetic field, which is detectable via light transmission. This allows for further understanding of the spin behaviors of 2D materials, as we're more capable of studying these degenerate quantum states which might be altered by a spin or other characteristics of the material. It is used within nitrogen vacancy center magnetometry, which is discussed further in our section on magnetic imaging, which puts into context how some of these discussed effects are utilized. Thank you.
Once you have your samples, how can we probe their functional magnetic properties and tell whether a given material would make a promising candidate for future spintronic devices? Well, we try to image the magnetism, but it's not easy. The image resolutions we require are far beyond what's achievable by conventional methods. Here, we'll take a look at two novel imaging methods that utilize quantum and magnetooptic effects. The first one for magnetometry, which is the mapping out of a magnetic field in space. The second one is to visualize the magnetic domains of our sample. First up is nitrogen vacancy center magnetometry, or NV center magnetometry. Take a microscope probe made out of diamond. An NV center is actually a defect in the diamond. It's one carbon atom being replaced by a nitrogen, and an adjacent one by a vacancy. So, how can we take advantage of a defect? Well, the NV center's ground state is actually a spin triplet state. The quantum number ms can take values of -1, 0, or +1. From the excitation by a laser, the spin state can be known by measuring the optical emission intensity when it relaxes back down to the ground state. With the probe over a magnetic sample, the energies of the ms sublevels are split by the Zeeman effect. Now, we can excite a transition from ms equals 0 to -1 or +1 with microwaves. And so if we can find the frequency of microwaves where we see an intensity drop in the optical emission, this indicates a change in ms and tells us the energy of the splitting, and hence the magnetic field at that point in space where the probe is. Here's a recent example of NV center magnetometry utilized in an atomic force microscopy setup to investigate a few layers of chromium triiodide. They found antiferromagnetic layering by mapping out the magnetic field, shown in the bottom left. A second imaging method is Lorentz transmission electron microscopy, or Lorentz TEM. Now, conventional TEM has been used for decades, but the Lorentz part refers to an adaptation for imaging 2D magnetic samples. Electrons passing through a magnetic sample are deflected by the Lorentz force. Now, it's important to note that in any electron microscopy setup, electromagnetic lenses use the magnetic field to focus the electrons. And in conventional TEM, the objective lens is situated at the sample. But here we'll have to turn that off because its magnetic field might distort the domains of our sample. Instead, it's replaced by a mini lens lower down called the Lorentz lens, hence Lorentz TEM. So let's picture that all together. Electrons are fired in from the top towards the sample. This sample has two antiparallel domains, and each of those will deflect the electrons differently from the Lorentz force. Then the electrons are focused by the Lorentz lens. The intensity across the screen gives us our image. Now, one thing to consider is that here the aperture has been positioned to produce a focused image. But unfortunately, this will always give uniform intensity across the image, so no contrast. In practice, there's a clever experimental trick to give us contrast, and that's to raise or lower the aperture a tiny bit, which will slightly defocus the image. But if you can imagine just raising the image plane, there, we'd see a dark fringe right where the sample's domain wall would be. Here's a recent example of Lorentz TEM in action on samples of Fe3GeTe2. From imaging the domains, they found a swirl in the magnetic moments. This is actually a quasi-particle called a magnetic skyrmion, and could theoretically be used in future memory storage devices. So these are just two of the nanoscale resolution imaging methods being tailored for use with 2D material samples. Further work will integrate these into new experiments and push the achievable resolutions even further.
To summarize, we've discussed the growing need for next-generation storage and processing technologies and some of the way 2D materials could be used to meet these challenges, as well as some of their key properties. 2D materials have many other exciting applications, from next-generation batteries to water purification, although these are beyond the scope of this project. We've touched on some of the fundamental physics behind these materials and computational and theoretical models of their properties. These can be used to search for materials with desirable properties such as high critical temperatures. We then moved on to some experimental methods used to produce 2D material samples, primarily exfoliation and thin film growth. Among these, liquid exfoliation and chemical vapor deposition stand out as being potentially scalable to high volume production. Finally, we looked at some of the magneto-optical effects displayed by 2D materials and their applications in imaging. Thank you.